Good evening, everyone. Welcome back to another lecture in the weekly colloquium series of Sci-Fi. Today, today's speaker is Arko Bhaumik. So Arko did his BSc from St. Xavier's College, Kolkata, and is currently pursuing the integrated PhD program at the Indian Association for the Cultivation of Science, Kolkata. He is now working with Professor Soumitra Sengupta, and the topic today is closely related to Soumitra sir's topic of research, which is also of interest to Arko. So Orko is mainly interested in theoretical cosmology and aspects of high energy physics and high energy theory. So today he's going to give us a glimpse of what one can refer to as the genesis of these extra-dimensional theories, that is the Kaluza-Klein theory. So I'm personally very thrilled about it. Without further ado, let's give the stage to Orko and let him take us away into other dimensions. No pun intended. So yeah, Orko, go ahead.
Yeah, okay. So thank you so much, Devan, for the introduction. And good evening, everyone. So can you guys hear me? Everyone can hear me, right?
Yeah, you're
Okay,
audible.
and this
Continue.
is visible to everyone, right? My screen?
Yeah.
Oh, okay. Just a moment. Yeah. So, okay, first things first. So thank you all so much for showing up today, of course. Now, before I go ahead and give you a brief overview of what I have planned for the evening, so I'd like to get a couple of things out of the way first. So firstly, as you surely know that we're going to be discussing the Kaluza-Klein theory tonight, right? So the original formulation of this theory, which was published almost a century ago from now, was for the most part an extension of the standard machinery of GR, so to say, to 5 spacetime dimensions. So that essentially makes it a theory of 5-dimensional gravity. It's not too noisy, right? It's okay?
Yeah, it's fine. Okay, continue.
Okay, so as such, I have practically had no choice but to assume that most of the audience today would be familiar with the fundamentals of general relativity. So we're going to be needing stuff like the geodesic equation, some concepts from space-time curvature, the Einstein-Hilbert action from which we can derive the Einstein field equation and stuff like that. So things that are usually covered in any standard first course in GR, so to say. So if you are not at all familiar with them, then even if the mathematical parts might appear to be a bit daunting, but you should be able to appreciate most of the physical ideas and the intuitive insights, nevertheless, that come along with them. And I have tried to give them special attention. So they should be pretty clear in this context. So that's the first thing. And the second thing is, and this should really go without saying, so if you happen to have any question or if you would like to contribute something, then please feel absolutely free to go ahead and make yourself heard. Well, as Doikan said, maybe keep it until the talk ends. And since I'm also new to most of these concepts, as Doikan already said, so this is kind of like my the topic of my master's project. So that would also serve as an important learning opportunity for me as well. So, and I personally feel that it's always better for this to be kind of an interactive session instead of being a one-sided monologue where I go on speaking and everybody else goes on listening, that kind of thing, right? Okay, so that being said, let us go ahead and have a look at the overview. So this is briefly what I have planned for this evening. So we're going to start by asking a few very basic questions about extra dimensions. So why we need them and that kind of stuff. So this part will be pretty qualitative. Then we're going to directly move into the nitty-gritties of the original Kaluza-Klein formulation, which is basically a theory of gravity in 5 dimensions. And we will see how it manages to unify classical gravity with classical electrodynamics. So this is what we'll be spending most of our time on, and we'll also see a couple of limitations of this theory, which it inevitably brings along with it. Then we're going to move to something called the Kaluza-Klein mass tower. And this is an extremely important concept as far as actual detection of these extra dimensions goes. And finally, we're going to end on a note of Braneworld scenario. This will be a pretty qualitative thing. I'm not going to go very deeply into the mathematical part of this. So we'll get there when we get there, this thing. So before I begin, I'd also like to say that the Kaluza-Klein idea is much richer and much more sophisticated in scope than anybody could probably hope to discuss within the span of an hour. So these are only the very basic concepts, the very basic aspects of Kaluza-Klein theory. Okay, so let's get into it. So extra dimensions, right? So the first question that should arise in context of any extra dimensional paradigm or that kind of stuff is, why do we need extra dimensions at all? So the answer to that is anything but trivial, right? So on one hand, it actually helps us unify certain physical theories. So these are certain far-flung physical theories of nature, and these are pretty much consistent in their own way. So they are consistent, they are highly successful within their own domain, okay? And they describe apparently unrelated physical phenomena. For example, we can consider gravity and electrodynamics, as we'll see shortly, within the traditional Kaluza-Klein concept. And this extradimensional paradigm kind of helps us unify such unrelated physical theories and actually see them as parts of some common super theory kind of thing. So we'll see an example of this firsthand very soon. That's what most of our time will be spent on. So this is one thing. And another thing is that this extra-dimensional scenario helps us resolve certain natural problems. Now, this thing is arguably more sophisticated in nature than this one. And these are some deep problems which have long plagued physics without any definite resolution yet. So we could ask, what kind of problems do they solve? So you could ask, this is a valid question, right? So the most prominent example of such a problem is the hierarchy problem. Now, what is the hierarchy problem? It's defined as a wide discrepancy among the characteristic scales of various fundamental forces of nature, right? So this is the definition of a hierarchy problem. And this is actually a class of problems of this kind. So let's look at a couple of examples of this so that this concept becomes clear. So this is the first example. Why is the weak force 10 to the power 24 times stronger than gravity? Of course, in spite of being called the weak force, right? So we know that there are four fundamental forces in nature, right? Gravity, electrodynamics, the strong force, and the weak force. Of course, with gravity, it's a bit dicey because we really know that general relativity would make us believe that gravity is less of a fundamental force and more a manifestation of the curvature of space-time, right? So for now, let's be lenient. So we'll consider gravity to be a force. So why is the weak force 10 to the power 24 times stronger than the force of gravity? Why is there such a huge difference in these scales, in the scales of these two forces? So that's one particular hierarchy problem. Another one is, why is the electroweak scale? So this is the scale of electroweak interactions, which we can usually probe in most particle colliders around the world right now. So of course, there are particle colliders which can go somewhat beyond this scale, but this is kind of an average thing. So the electroweak scale is of this order, is 100 GeV. But the Planck scale, which is the theoretical scale at which quantum gravity effects are thought to become manifest, so that scale is of the order of 10 to the power 19 GeV. It's a huge thing, right? It's nowhere even close to what we can achieve in near future. So there is a 10 to the power 17 order of magnitude difference between these two scales. Again, there is a hierarchy, as we see. So extra-dimensional scenarios actually, so by the time we end, we'll actually have an intuitive idea of how certain extra-dimensional paradigms help us resolve such hierarchy problems quite naturally. We'll not go into the mathematical details of that, but I'll share some physical intuition about that. Okay, so now let's address the elephant in the room. So we're basically saying that extra physical dimensions exist all around us, right? So they can exist all around us, right? So, why can't we see them? So we should be able to see them like we see the X, Y, and Z dimensions, right? The three spatial dimensions. So why can't we see these dimensions? So in order to explain this, we have to invent something, some idea to explain the invisibility of these extra dimensions, right? And that idea actually goes by the name compactification. So this is a common feature of many extra-dimensional theories. And what it basically says is that the extra space-like dimensions in these extra-dimensional theories, these are assumed to be curled up. These are assumed to be compact and kind of periodic. They're curled up on themselves with an extremely small length scale. And this extremely small length scale is what effectively renders them invisible to our eyes. So these are not like the open, unbounded X, Y, and Z dimensions, like these macroscopic dimensions that we're used to in our regular four-dimensional world. So these are curled dimensions. And what do we actually mean by that? So again, let's look at an example of that. So this is a very simple example, this kind of a topology. So this is actually M cross S1, and this is actually what Kaluza-Klein originally considered in their theory. So this is courtesy Kaluza-Klein, of course. And what do we mean by this? Well, this means M here is our usual four-dimensional, so 3 plus 1 dimensional space-time manifold, which you can see of GR. And S1 is a circular dimension, not exactly a circle, so a circular dimension which is attached kind of orthogonally to every point on M. So what do we mean by that? So we'll see what orthogonally rigorous means once we get there very soon. So for now, we can of course define this mathematically, right? So we can define, of course, an n-dimensional Euclidean space, right, with n mutually perpendicular axes. So the mathematical definition, of course, goes way beyond what we can visualize. So it's kind of like that. So and of course, one of the most important things that physics actually teaches us, mortals, is that we can't always rely too much on our visualization skills, right? So this is kind of an orthogonal dimension. We'll see that, of course, very soon, what it really means. And we assume the radius of the circular dimension to be of the order of the Planck length, which is roughly 10 to the power minus 30 centimeter, or like that. So this extremely small length scale is what actually renders this dimension invisible to our eyes. And before we proceed any further, let's make another note. So this is kind of a factorizable topology. So what do we mean by that? This is kind of a product space, right? So we have M. M is an independent manifold or usual regular manifold. And S1 is an additional circular dimension, and that is attached to M at each point. So this is kind of a product thing, right? A product of two spaces. And that is what we call a factorizable topology. And non-factorizable, so non-factorizable topologies also exist. They can be considered, and they also prove useful very often nowadays, particularly in modifications of the KK idea, Kaluza-Klein disease, and in certain modern extradimensional theories. So one of them is the Randall-Sundrum-Braneworld scenario, which we won't study right now in this talk, but I'm mentioning this as a passing comment. So that is a very important example of a non-factorizable topology, unlike this one. So that kind of spurred new interest in extradimensional scenarios in 1999. Okay, so so now it's time to move directly into Kaluza's proposal. So Theodore Kaluza published this proposal in 1921. So at that time, the only known interactions of nature were gravity and classical electrodynamics, right? So the strong and the weak forces obviously hadn't been discovered yet. And even quantum mechanics, if you look at history, it was virtually in its infancy. Well, not exactly infancy, in kind of its adolescence, finally. So it might be called a very limited theory from our current perspective, but at that time it was a pretty huge thing. It was monumental, right? Because it sought to unify the only known fundamental forces of nature at that time. So what was it that Kaluza said? Let's look at that. So Kaluza said we have a regular 4x4 matrix, right? Which represents a 4-dimensional metric tensor. So Kaluza said, let's go ahead and extend this metric to a 5-dimensional version, where this, of course, can be represented by a 5x5 matrix of this form. So in component form, you will see that this 4x4 block is nothing but our ordinary 4-dimensional metric tensor. And in addition to that, we have certain components which come from the 5th-dimensional contribution. So in component form, it's basically given in this form. This is a block form. So we'll see why we denote this by A. So it actually has something to do with our Maxwell 4 potential. We'll see that very soon. And this is kind of a convention that we would like to follow from now on. So extradimensional things, extradimensional entities are usually denoted with a tilde on top. So every extradimensional entity that we're going to encounter from now on, we'll denote them by a tilde on top. And of course, these are capital Latin indices, right? So we'll assume that these kinds of indices can run over 5 values actually, as opposed to the 4 values that Greek indices can run over. So this is a convention that we'll follow. Okay, so this is of course the component form of this metric. And so before we proceed any further, you could very well ask what happened to the mu4 and the 4,4 components, right? So mu and nu can both run from 0 to 3, right? 0, 1, 2, 3. So what comes after that? It should be g tilde mu4 or g tilde 4 mu or g tilde 4 4 like that. So what happened to those components? The answer is it's purely a matter of convention. So as it's kind of a silly convention actually, but as it's the proverbial 5th dimension that we're talking about, so we skip the index 4 and jump to the index 5 straight away. So nowhere from now on will the index 4 have any role to play in our analysis. Okay, so there are 2 important points that we must keep in mind before we proceed. The first thing is, for now, A mu is simply defined to be a component of the 5D metric tensor. Now, for now, it has nothing to do with the Maxwell 4 potential yet. So I said there is a connection, but for now, we are not allowed to make any assumption in regard to that connection. So let me briefly go back to that metric. So A mu is defined exclusively according to this relation. So there is no connection with the Maxwell 4 potential yet. In fact, that is what we would like to see. That is what we will see. That is what actually emerges from this kind of a setup without any a priori assumption with respect to that. I'm sorry, just a moment. Yeah, okay. So this is the first assumption, right? And the second one is this Okay, so the justification of this first assumption actually comes only in hindsight, when we actually see that AMU will play a role analogous to what the Maxwell 4 potential is in 4 dimensions. For now, there is no connection, apparently. So the second point that we must keep in mind is that the 5-5 component of the metric, the lower right component, which we put to be equal to 1, in a most general setting, it need not be 1. It can, of course, be an arbitrary scalar field phi x, right? Which can depend on all 5 spacetime components, right? All 5 spacetime coordinates. So in general, for a 4D metric, the metric components can depend on all 4 spacetime coordinates. So since we are simply extending that idea to 5 dimensions, we must assume that all those components can depend on all 5 spacetime coordinates. So phi x should be of this form. The g tilde phi 5 component should be of this form, which can later enter our equations of motion. So this should actually be a field with its own life, its own dynamics. So why are we assuming this to be 1? Again, this is actually a historical choice, which was actually made by Kaluza-Klein in their own formulation, in the original version of the theory. So we're going to stick to that one. And actually, this will turn out to be a limitation of the original formulation, as we'll see later. Okay, so now comes one of Kaluza's most significant contributions. This is the cylinder condition. Now, this condition basically says that no component of the 5-dimensional metric can depend explicitly on the 5th-dimensional coordinate. Why is that? Well, if this seems kind of ad hoc to you, that's because it is. Because this was actually imposed by Kaluza to explain in an ad hoc manner why no observable phenomenon actually depends on the presence of an extra dimension. But fortunately, we'll see how to explain this physically soon after we meet Klein's modification in this context. So for now, let's just keep this in mind. So no component. So in general, all components of the 4D metric can depend on all 4 spacetime coordinates, right? So this is in contrast to that. No component of the 5D metric can depend on the 5th coordinate. So let's just keep this in mind from now on. Okay, so the merit of Kaluza's own formulation was that based on these ideas alone, Kaluza actually managed to show that the equations of 5-dimensional gravity actually reduce to equations of 4D Einstein gravity, which we're usually familiar with. So these are the equations of GR basically, in presence of an external electromagnetic field. And AMU there actually plays the role of the Maxwell 4 potential. So this was actually Kaluza's own, the merit of Kaluza's own derivation. But there were 2 severe limitations of Kaluza's formulation. So the first one was that if you take that metric, that 5x5 metric, then the inverse metric is extremely cumbersome to compute. So let me again go back briefly to that one. So you basically have this metric. So you can only imagine what its inverse is going to look like. You have to take the determinant of this, take the reciprocal of that. There is all that business with cofactors and minors and everything. So in absence of any additional assumption, this is going to be a huge thing. And every metric component, which is every contravariant metric component, G tilde AB, uppercase AB, that is going to have an extremely ugly looking form, right? So that is pretty much useless for most practical computations. So that's the first one. And the second thing, which I already said, is that the cylinder condition in this context appears to be a rather ad hoc assumption, right? And that is actually where Klein comes to our rescue with his modifications. So due to these limitations, these 2 limitations, we are not going to study Kaluza's original proposal, but we are only going to study what Klein actually gave us after Klein modified Kaluza's own formulation. So let's see what Klein's contributions were. So Klein published his results 5 years after Kaluza published his own. And the first thing that Klein did was he actually modified Kaluza's simple looking metric to this form. I'm sorry, there seems to have been a slight formatting error with this thing, so it appears kind of hazy. I guess it's legible though, right? So he actually modified this metric. So this 4x4 block no longer corresponds to the 4D metric anymore. Instead of that, we have something much more complicated. And this 5-dimensional thing, this column and this row remain the same as they were in Kaluza's proposal. But this 4x4 block gets modified according to this definition. And although this looks much more complicated than Kaluza's proposal, there is actually a very nice trade-off in here. So what is the trade-off? The inverse metric of this thing, if you try to compute the inverse of this, the inverse metric components are now much simpler to compute. So the inverse components are simply given by this formula. So you can actually check these things. So either you can take this component by component and try to multiply these things together and check if that gives you something like delta AB. If that is the case, then you are done. Or like I did, you could try to construct the explicit matrix, feed it into Mathematica, feed both matrices into Mathematica or something like that, and check if that product gives you a 5x5 identity matrix, right? So if that's the case, then you are done. So it is actually the case. So you can check this directly. So this is actually the trade-off. So one question that you could immediately ask is that it's all fine, and in the end, it is a nice trade-off. The inverse components are like this, but where does it actually come from? Where does this thing actually emerge from? It has to come from somewhere, right? So for that, let's look at a very simple derivation of this metric. So I have included it because once we have that, the rest is actually like clockwork. Once we have the metric, the rest is actually very straightforward. So we can do all kinds of manipulations with it, as we do in general relativity. So let's spend some time on this derivation. So this is a simple derivation. So let us define a vector like this in 5D spacetime. So this is dxa ea, where ea are the basis vectors. Okay, so before I go any further, so you should be careful who you show this to actually, particularly if you show this to a pure mathematician. And if there is a mathematician among us today, I'm already doomed, I'm sure of that. Because all jokes apart, because to do full justice to such an idea, you rigorously need differential geometry, which immediately makes things like this ea basis vector and stuff like this superfluous and obsolete, like, right? So we need to consider, we need to upgrade to stuff like tangent spaces and connections to replace these simplistic things. So on the other hand, the actual merit of this derivation is that in spite of its extreme simplicity, which we can all understand, it actually manages to get the key ideas across, and we can get a concrete idea of how Klein's modified metric form actually emerges. So anyway, let's get on with it. So we have this thing. And now, in order to get ds tilde squared, which is the 5-dimensional spacetime interval, you just take the dot product of this with itself, right? Again, this is a very fishy concept because the dot product usually isn't defined concretely in the context of a general manifold. So you have to do some very, you have to get some pretty intricate details out of that manifold before you can define something like vector products. Again, let us ignore that for now, and let us assume the manifold to be well defined enough for us to be able to do this. So ds tilde square is actually given by this. This is the definition of ds tilde square, right? And if you compare these two, then g tilde ab is actually given by the dot product, whatever that may be, of these two basis vectors, right? ea dot ab. Okay, fine. Now, unlike Kaluza's original proposal, we don't assume 4D spacetime to be completely orthogonal to the 5th dimension right now. Instead, we assume that each 4D basis vector can be decomposed in this form, where this is a longitudinal component and this is a transverse component. And what are their properties? Their properties are defined by these relations. So the transverse component is orthogonal to the 5th basis vector, and the longitudinal component is parallel to the 5th dimensional basis vector. We can do this, right? We can write any vector in this form. So once we have this, then we can immediately figure out what, yeah, again, there is a formatting issue. I promise it will get a bit better once we proceed. So this region is a bit hazy. So in order to figure out what k is, this proportionality constant is, we can simply take the dot product on both sides with E5, right? And E5 dot E5, according to this, is nothing but g tilde 5, 5. And E mu longitudinal dot E5, according to this, E mu transverse dot E5 is 0 anyway. So E mu dot E5 is nothing but this part alone dotted with E5, and that gives us, according to this, g tilde mu 5, right? So k is obviously g tilde mu 5 divided by g tilde 5, 5, like this. And plugging it into this equation, E mu longitudinal becomes this. So this is pretty straightforward. So let's keep this in mind because we're going to need this very soon. And again, on the other hand, physical intuition now tells us that the extra dimension that we have, it should be orthogonal to our observable spacetime, right? Because there has to be some physical intuition as to why we can't observe it, right? So to reconcile these two insights, we kind of assume the 4D metric to be determined completely by the transverse components of the basis vectors alone. So unlike in Kaluza's proposal, G mu mu is no longer given by E mu dot E mu. Instead, it's given only by E mu perpendicular dot E mu perpendicular. And this is actually what brings about all those extra terms, as we'll see now. So we have G tilde mu 5 according to the definition. So it was E mu dot E mu. So E mu is this whole thing, E mu is this whole thing. So we need to take the dot product, right? So this first term dotted with the last term is 0 anyway. This is because these are mutually perpendicular, right? Similarly, the second one dotted with the third one is 0, right? So the only contribution comes from the first one dotted with the third one plus the second one dotted with the fourth one. And the first one dotted with the fourth one, third one, sorry. The first one dotted with the third one, according to this relation, gives us G mu. And this one dotted with this one gives us this thing, right? So because we essentially substitute this thing right here. And that actually gives us this. So there was an additional E5 here. So E5 dotted with E5 again cancels one factor of G tilde phi phi from the denominator, and we're left with this. The rest is pretty straightforward. We define A mu to be equal to this thing and phi to be equal to this thing, the scalar field, and we immediately arrive at G mu nu equal to G mu nu tilde equal to G mu nu plus phi A mu A mu. And the rest is pretty straightforward. And this is also, this comes directly from this. And finally, we can substitute phi to be equal to 1, which is actually in line with what Kaluza originally proposed. And that gives us Klein's metric kind of on a platter, right? So this is basically the derivation. And yeah, so this is it. So another property of Klein's metric that will become useful to us much later is this property. So if you take the determinant of the whole 5D metric, then that determinant kind of magically is equal to the determinant of the 4D metric alone. So there, all the terms containing A mu and stuff like that, they get cancelled. Again, this is something that you can check. So again, just bear with me. I'm going to go back to that metric. Okay, so this metric, right? So if you take the determinant of this metric, you will see that this is a 5 cross 5 determinant. This is a very complicated thing. So if you do that, you will see that every term of the form of like, which contain cross terms of A with these metric components, or A dotted with itself, A multiplied with itself, all kinds of those terms are going to vanish. And we are going to be left with simply the determinant of what our usual 4-dimensional metric is in standard general relativity. So this is another very important property of this modified metric. And it wasn't the case in Kaluza's original metric. So yeah, and it will actually be useful to us at the very last step of our unification attempt. Okay, so this is arguably one of Klein's most important interpretations. So Klein actually interpreted the extra dimension to be a circle, which is of the radius of Planck length. So that is, I told you, that is of the order of kind of 10 to the power minus 30 centimeter kind of thing. So this kind of physically explains why we can't observe the dimension, right? Because, you know, it's straightforward, it is so small. And it also gives the cylinder condition a physical justification. So because of this extreme small radius of this extra dimension, so it's only reasonable to assume that no macroscopic phenomenon can depend explicitly on the presence of this extra dimension, right? And if this is a circle, then the independence of this of the metric components of this fifth dimension actually introduces a kind of cylindrical symmetry, right? Because no metric component is actually dependent on the coordinate which we can measure along the circumference of this extra circle, the circular dimension. So it also gives the cylinder condition a kind of physical justification and also explains its name. So these are the two very important contributions of Klein's modification. Okay, so that's fine. And why is, excuse me? Was there a question?
No, go ahead. Yeah.
Okay, I'm sorry. So, yeah. So why is it a quantum thing? It's because Klein actually explained the quantization of electric charge in terms of integral multiples of the fifth dimensional momentum. This is what this is something like Bohr actually did. So he actually assumed standing waves and that kind of thing in old quantum theory, and that gave us Bohr's quantization condition, right? So Klein did something similar to this, and we are not going to deal with this very explicitly in this talk, because it actually kind of deals with the coupling of fermionic fields in 5 dimensions and stuff like that, and that is beyond the scope of this talk. So this is also kind of a remark. That is what gives this, that is what quantum actually means in this context. So, and this actually also introduces one of the most significant drawbacks of Klein's theory, Kaluza-Klein theory. So we'll get to that later when we discuss the limitations. Okay, so now we can deal with the 5-dimensional geodesic equation, because now we have the matrix. So I spent quite a lot of time on the basics, but it's okay, because now once we have the metric, the rest is going to be pretty straightforward. Okay, so we know how we can derive the geodesic equation in the context of GR, right? So we basically have to extremize something like the proper time. And in the general context of GR, this proper time gets replaced by a more general thing called the affine parameter. So this is basically the particle action in GR. If you replace this by eta, then that becomes the regime of special relativity, right? So if you extremize this thing with respect to the particle coordinates, then that immediately gives you the geodesic equation. And note here that all the indices are capital Latin indices. So these are intrinsically, these are 5-dimensional quantities that we're talking about. So the 5-dimensional Christoffel symbols that appear here are exactly defined as they are, as their 4D counterparts are defined. So this is how they're defined. And all the indices are, as usual, the Latin indices. So first, let's take this equation. Let's take this equation and let's first focus on its four-dimensional subspace components. So let's put A equal to alpha. So that means we are focusing on the subspace components, right? Now the sum is still runs over 5 indices, right? Because the sum was over B and C, right? Okay, so I know that this might seem like a whole lot of mathematics right now, and we apparently, it might seem like we have no clue what we want to do with that. But if you bear with me for a few more minutes, then we'll see something absolutely fascinating emerge out of all this mess. So you need to trust me at this point. So we have this sum, right? So we can immediately expand this sum in this form. So here we have actually taken B to be equal to beta and C to be gamma. And this is actually the subspace component of the Christoffel symbols, right? And these are the cross terms. So B is beta and C is 5. So this is nothing. So since this is symmetric in B and C, so a factor of 2 comes outside. And finally, we have both B and C to be equal to 5 and 5, and it's this. So this is the same thing, just in an expanded form. So, and now we have 3 kinds of Christoffel symbols in this equation, right? And we also know Klein's metric. So we can immediately plug that metric into this definition of the Christoffel symbol, right? And we can actually compute these Christoffel symbols. And I'm not going to show you the detailed calculations because they're pretty lengthy. So I'm going to show you only the end results because that's what matters mostly. So the 3 kinds of Christoffel symbols are given by these 3. So this is this, and this is fortunately for us equal to 0. And here we have something like F. And F here, although it looks like something to do with the Maxwell field strength tensor, the 2 form F here is just the exterior derivative of A. So like A, it doesn't have anything to do with the 4D Maxwell 4 potential yet. In fact, that is a connection that we'll see soon emerges from this kind of a theory. So we have these components, and if we plug them in here, so F is now just, F mu nu is just del mu A nu minus del mu A nu, that kind of thing, like we define usually. So the 3 kinds of Christoffel symbols are these, and if we plug them in this equation and simplify things, then we're going to end up with something like this. And this is what the 4D subspace component of the 5D geodesic equation, it looks like. And now we're done with this. And now let's look at the 5th component similarly. So by now you know the drill. So we put A equal to 5 and we expand again in the same way. There are 3 kinds of Christoffel symbols emerging. And we can also compute these Christoffel symbols explicitly using Klein's metric. And these are arguably a bit more complicated than what we obtained earlier. So they are of this form. And again, this component, fortunately for us, is equal to 0. Now, again, we take these 3 things, substitute them in here, here, and here. And if you simplify that equation, then we get something like this. Yeah, this is ugly, I know it. But there is something fascinating about the pair of these equations. So now let's look at both equations side by side. And if you are keen, you will immediately see some kind of symmetry in between these 2 terms, right? So apart from the fact that it has been contracted with A alpha, this term and this term are exactly the same and appear with opposite signs, right? So if we contract the left-hand side of this equation and add these 2 equations together, then this term is going to cancel this term. And on the left-hand side, we're going to have A alpha d2x alpha ds tilde square plus only this one. And also on the right-hand side, this whole thing is the same as this whole thing, right? And here also, if we contract this term with A lowercase alpha and add these 2 terms together, then due to the antisymmetry properties of A, these whole things are going to cancel each other, right? It might not be obvious right away, but if you do that, if you try to raise an index of alpha here and lower an index of F, then it's going to give precisely this term with a minus sign. That's what I'm saying. So these 2 terms are going to cancel each other. And we're going to be left with only this term on the right-hand side. So let's write what we get. So we're going to basically get this thing after contracting this with A alpha and adding these 2 equations together, where I have obviously shifted this thing to the left-hand side, so it's a plus sign. And this thing within this pair of square brackets, what is this? This is actually the total derivative of A alpha with respect to S tilde, isn't it? Because this is just the chain rule, right? This is del beta A alpha dx beta ds tilde. Of course, for the chain rule to hold, there has to be a term like del 5 A alpha dx 5 ds tilde, we'll say. But remember the cylinder condition, del 5 A alpha is obviously 0 because A alpha is basically a metric component and no metric component can depend on the 5th dimension. That was what we basically postulated, right? So this is d alpha ds tilde, this is dx alpha ds tilde. And here we have A alpha and the second derivative of X alpha. So this whole thing plus this whole thing can actually be written as dds tilde of this thing, right? This is just the product rule of derivatives. So it gives these two terms. Plus we have dds tilde of dx5 ds tilde, like we have here, right? So that is equal to 0. What is the advantage of writing it this way? So this way we can actually express the left-hand side as a total derivative of something. And since that total derivative is equal to 0, so this something must be a global constant, isn't it? And we can denote that constant by xi. So this is xi, right? I always get confused between xi and zeta. Anyway, so I guess this is xi. So if this can be written as a constant xi, then we can immediately write dx5 ds tilde as xi minus this thing, right? And what is the advantage of doing that? The actual advantage of doing that is that it allows us to write the 5D momentum kind of thing, this thing, entirely in terms of 4D components alone. So it can effectively eliminate the effect of the fifth dimension from this equation. Because now if we go back and substitute this thing in here and simplify things, then this is what the fascinating thing looks like that we're going to get. We're going to get something like this. Now this should immediately appear familiar because this looks a lot like Lorentz force law in curved spacetime, isn't it? So this is the geodesic equation, and this looks like the source term, the field strength tensor. And this actually looks like the Lorentz force law, this whole thing. But there is a serious problem here because these derivatives are all with respect to S tilde, the 5-dimensional affine parameter. But in order for this to be a proper Lorentz force law, we need this to be, these derivatives to be with respect to the 4D affine parameter, right? S tilde. So what can we do at this point? We can do something. We can try to figure out a relation between S tilde and S. So if we can write S as a function of S tilde, that will allow us to replace these derivatives with those in terms of S, right? So let's try to find a relation between them. So ds tilde square is defined as this, right? And so if we plug in the definition of G tilde AB, what we obtained earlier, Klein's metric, then we're going to get something like this if we expand this thing out. So you can check it actually. And this part is nothing but G mu nu dx mu dx mu, which is the 4-dimensional interval. Plus, since G tilde mu nu is equal to G mu nu plus A mu A nu, this is the contribution of the A mu A nu term. Plus there are two cross terms of this form. Plus there is a G tilde 5 5 dx 5 dx 5. Since G tilde 5 5 is 1, we have this thing. So this is pretty straightforward. We just need to expand this and keep our definition of the metric in mind. So now if we substitute in this definition, this thing, this differential, then, okay, so where are we getting this from? We are getting this from this thing. We're actually taking the differential on both sides. So dx5 is xi ds tilde minus a alpha dx alpha. This is just a differential. So if we substitute this in here, and we simplify things down to the bare minimum, then we're going to see something surprising. All the terms that contain a mu and these cross terms of this form, they are going to cancel each other. And we're going to be left with a simple proportionality relation like this one. So ds tilde is actually proportional to ds. And the proportionality constant is given by this thing, root over 1 minus xi square. And once we have this, we can immediately rewrite these derivatives, right? So for example, dx beta ds tilde becomes dx beta ds times root over 1 minus xi square. And if we go ahead and do that with all 4 terms, the second derivative term and all these 3 first derivative terms, then after simplification, okay, there's a serious formatting issue in here, but I hope it's legible. So we're going to end up with something like this. And this actually looks like the Lorentz force law. There is no problem with the derivatives anymore. And we also have a proper proportionality constant here. And this actually has the correct form of the Lorentz force law. So that is something which should make us very happy. So in order to identify it more strongly, the Lorentz force law, let us make this identification. So if we write xi to be equal to this, where m and q are the mass and charge of a particle moving in presence of such a field, then this constant is equal to q by mc. And once we do that, it gives us exactly the Lorentz force law. There is no more confusion about it. So what is the bottom line here? So we did all this math and we got this. What is the bottom line? The bottom line is we started from the vacuum geodesic equation, right? And we ended up with the geodesic equation in presence of an electromagnetic field in 4 dimensions, which is basically, in other words, the Lorentz force law in curved geometry, right? So we already have a kind of unification, which is at the level of the equations of particle motion, right? So particle moving in 5-dimensional vacuum actually appears to be moving in the presence of an electromagnetic field when we look at it from our 4-dimensional point of view, isn't it? And f alpha beta here is actually it is apparently the contribution of the fifth dimension alone. So that is the kind of unification, tentative unification, which we have arrived at. So does that actually mean that we have managed to unify gravity and electrodynamics? Well, the answer to that is unfortunately no, not yet. And in order to see why not, we need to look at two distinct aspects of classical field theories. So on one hand, we wish to study the motion of a test particle in presence of an externally applied field, right? And the definition of a test particle, of course, varies from field theory to field theory. For example, in GR, it has to be a particle of negligible
Orko,
mass.
you have 10 minutes.
Oh, God.
You have
Okay.
10 minutes, okay?
Okay, I'll try to wrap up.
Oh, yeah, okay.
So
Yeah,
the motion of a
fine.
test particle in presence of an external field. So this test particle can vary from, this definition can vary from field theory to field theory, right? So in GR, we have a particle of negligible mass, which qualifies as a test particle, so that it doesn't end up producing gravitational back reactions on itself. So these are encapsulated in the equations of particle motion. So these are some examples of such equations. So the Lorentz force line EM theory, the geodesic equation GR, etc. But there is another aspect, an arguably more important aspect of field theories that we haven't considered yet. So that is the dynamics of the field itself, which is governed by variable source terms, which can vary in space and time, right? And those are encapsulated within the field equations. And examples of such field equations are the classical Maxwell equations, the Einstein field equations in GR, like that. So we need to check, excuse me. Okay, so we need to check these field equations, whether this tentative unification that we have seen at the level of the equations of motion, if that unification carries on to the level of the fields themselves. Only then we can say that we have achieved a kind of complete unification, right? So let's see that. So for that, we need to consider the 5D Einstein-Hilbert action. And if you are familiar with GR, you will immediately say that we have merely extended the idea of the 4D Einstein-Hilbert action to 5 dimensions. This R tilde is the Ricci scalar, which is defined in this way. And R tilde AB is the Ricci tensor, which is defined in this way. These are completely analogous to what we do in standard 4D GR. So if we go ahead and do this, so if we, so by now you know the drill, right? Okay, just a moment. I think someone is trying to say something.
Yeah, go ahead, Orko.
Okay.
That's fine.
Okay, I'll get to your question, Shadnik, by the end. So, okay. So by now you know the drill, right? So we expand this thing out in terms of, so we have basically have three types of Ricci tensor components, right? So we basically expand this thing. And once we have the metric, we can once again write this thing in terms of, we can actually compute these three components, right? Starting from Klein's metric. So those are some truly monstrous things. So I'm going to give you a glimpse of that. R tilde mu nu is something that looks like this. Yeah, so there is absolutely no way that I'm going to show you all the steps of this monstrous calculation, right? So it's horrible, and it's particularly horrible because it's not difficult at all. It's just extremely cumbersome. So you have to keep track of a lot of indices, make use of the antisymmetry of F from time to time. And even then you end up with something as large as this one. So if I try to show you all the steps, you will run out of patience and I'll run out of time. So I'm not even going to attempt that. So R tilde mu nu is this thing. And it is the sum of this whole additional thing and the conventional 4-dimensional Ricci tensor, which will become useful right away. And R tilde mu 5 is something like this, and R tilde phi 5 is something like this. And these nabla operators are basically the covariant derivatives, as opposed to the coordinate derivatives that we have seen so far. So if we take these things and we plug them in here, here, and here, and we also make use of the inverse metric components of the Klein's metric that we defined earlier, then we end up with something absolutely beautiful. All these things get cancelled, and then all we have left is this thing. So the 5-dimensional Ricci scalar is simply the sum of the 4D Ricci scalar and something that looks like the conventional 4-dimensional Maxwell Lagrangian, right? This is what we basically derive the Maxwell field equations from, right? In standard EM theory. So we can immediately take this thing and try to substitute it here. And at this point, we have to take the help of an old friend who we left behind. And that old friend comes in the form of this fact. So G tilde is equal to G. We mentioned this earlier, right? So the determinant of the 5D metric after Klein's modification becomes equal to the metric of the 4D subspace metric, right? So what we actually made in standard GR. So if we do that, this minus G tilde actually becomes root minus G. And we have split d5x into d4x and dx5. And this is basically R tilde. Now, what is this thing? This first part actually gives us what? This actually gives us the standard four-dimensional Einstein-Hilbert action. And this second part actually gives us the Maxwell action. And what about this thing? What do we do if this thing diverges? So we have to revisit another old friend at this point, which is compactification. So if we assume the fifth dimension to be a curled up dimension, then this dx5 actually doesn't diverge, unlike some dx or dy or anything of that sort, which we encounter in our day-to-day lives. So this dx5 in that case, since S1 is a circle, this dx5 actually gives us simply the circumference of the circle, right? And this SEH tilde, this Einstein-Hilbert action in 5 dimensions, actually becomes simply proportional to the Einstein-Hilbert action in 4 dimensions of ordinary gravity and the Maxwell action, with the proportionality constant being something which scales as the radius of this extra dimension. And the bottom line here is that we started from an action of pure gravity and we end up with gravity and electrodynamics, right? At the level of the fields themselves. So this unification is kind of satisfactory at this point, right? So before we get too happy about this, so I'll briefly gloss over this. So there is something that we must remember, that from our knowledge of ordinary electrodynamics, we have to recall a very important concept, that of the gauge invariance of the Maxwell four potentials. So any kind of physics must remain unchanged under this kind of a transformation, right? So this is the property of gauge freedom from Maxwell electrodynamics. And in order for this unification to be complete, like we showed earlier, that electrodynamic properties emerge from the contribution of a fifth dimension. So this gauge freedom property must also somehow, we must be able to show that each somehow also emerges from 5D geometry, right? So in order to see that, let us transform the fifth dimensional coordinate in this way. So this is basically a translation, right? And if we do it in this way, then how does dx5 change? So obviously delta x5 is given by this thing, right? So how does dx5 change? So since d and delta commute, this is basically d of delta x5, and delta x5 is nothing but this. So this is d of zeta, and d of zeta is basically, due to the chain rule, d of zeta is given by this. So let's keep this in mind. Now, we must recall that we defined ds tilde square like this when we were studying the relation between ds and ds tilde in the in our 4D, when we were studying the 5D geodesic equation, right? In order to rewrite those derivatives with respect to s tilde. So in here, we have this thing. So if we take delta on both sides, so we have simply taken delta on both sides to see how both sides transform under such kind of a coordinate transformation. And if we do that, then note that our 4D coordinates have remained unchanged. So ds square shouldn't have changed in any way, shouldn't change actually. So delta of ds square is actually going to give us 0. So we're going to be left with this. And here we have dx5, delta of dx5 here and in here. So if we go ahead and substitute this thing in here, and we kind of simplify everything down, then we're going to be left with something like this. And at this point, we introduce this assumption. We impose this condition that ds tilde square remains invariant under such a coordinate transformation. And this basically means that such a transformation is a symmetry of ds tilde square, right? So delta of ds tilde square should be obviously equal to 0 under this assumption. And if that is to hold, then on this right hand side, this is the only term that can be identically equal to 0, right? Because this can't obviously be 0, because dx5 and dx mu are independent space-time separations, right? So this is the only thing that can be 0. And if this is 0, which is given by this condition, then we immediately get this property that a mu actually transforms like this. And this actually gives us the condition of gauge freedom, isn't it? So the bottom line here is that we start with coordinate freedom of the 5-dimensional space-time interval, and we are left with gauge freedom in 4 dimensions. So it kind of hands us with gauge independence on a platter, right? So that's the thing. So this is actually a very deep idea, and in order to see that, let's look at the same thing from a slightly more abstract point of view, okay? So in order to do that, first we need to define what the isometric group of a space is. So the intuitive idea is at least very clear. It is the group of all distance preserving transformations, coordinate transformations, of course. So for example, on S1, if you take 2
Orko, I'm
points,
sorry to interrupt, but you have like only few minutes left.
Okay. I'll try to make it fast. Okay. So yeah, after we're done with this, I have only a very brief thing to go on. So this is the basic idea. So for S1, we simply have the isometric group is this, because if you have 2 points on a circle, then basically if you rotate them through the same angle, then the space-time, then the spatial separation between them actually remains invariant, right? And SO2 is an abelian group with a single parameter, which is obviously isomorphic to U1. So we also know that electrodynamics is a U1 gauge theory, right? So is this actually a coincidence? The answer is that no, it's not a coincidence. It's actually a general feature of many Kaluza-Klein like extradimensional theories, where actually the isometric group of the compactifying manifold actually translates into the gauge group of the emerging theory. And if this is the idea, then you can immediately ask, is there any way that we can get to non-abelian gauge theories from compact abelian manifolds? And in fact, we can, because there are certain techniques in string theory that allow us to do that, but they are far beyond our scope, at least the scope of this talk. And right now it's obviously far beyond my scope because I'm also running out of time. So it also goes way beyond what Kaluza and Klein's original idea was that we're interested in. So I'm going to leave this as a remark right now. Okay, so these are the limitations of the Kaluza-Klein theory. So firstly, as I told you, the phi-5 component is assumed to be a constant, whereas it can generally be assumed to be a field of its own. And this is actually called the dilaton, and it has something to do with stabilizing the radius of the fifth dimension in many cases. And we obviously ignored that one. So that's the first limitation. And also we didn't go into the behavior of fermionic fields, right, in 4+1 dimensions. And such a treatment, I don't remember if it was actually Klein who did it or someone immediately after him. But if you try to do that, then you actually end up with a calculation which predicts the electron mass to be of the order of 10 to the power 30 MeV, as opposed to the actual mass of 0.51 MeV. So the electron mass actually comes out to be of the order of the Planck mass. So this was one of the earliest known and most significant drawbacks of the original KK formulation. And the final thing was that theory was conceived almost 100 years ago when gravity and electrodynamics were the only known natural forces. So later attempts were made to accommodate the other forces, but they also failed on several occasions. And one such effort was actually made by Pauli himself. But even then he faced insurmountable odds and he had to give up on that idea. And as a result of this, the KK vision was mainly abandoned for years, until its core ideas found new impetus within the domain of string theory. So, Doipan, are you there? Hello?
Yeah.
Okay, so I'm going to need just 5 minutes tops. Okay, after
Okay,
this.
fine. Okay, fine. 5
So,
minutes.
yeah. So, okay, now I'm going to very briefly go over something called the Kaluza-Klein tower. So this is a very important concept as far as the actual detection of these extra dimensions goes. So we first need to define what a bulk field is. So a bulk field is a very, its intuitive idea is pretty clear. So it's a field which can propagate through all the extra dimensions in addition to our 4 observable dimensions. Now, if we compactify on S1 is a circular dimension, right? So obviously everything remains periodic under a transformation of this kind. So this basically means you are starting from one point on the circular dimension, and after going around the circle once, we're ending up on that same point. So all physical fields must remain invariant under such a transformation. So now if we take phi to be a bulk field of this form, which is a function of all coordinates, then we can obviously write a mode expansion of the bulk field of this form. Okay, so this is kind of a Fourier expansion. So if phi depended only on y, these things would have been constants, only the Fourier coefficients, right? But since this is also dependent on x mu, this dependence has to go somewhere, and it goes into these coefficient functions. And these actually appear to us as 4-dimensional individual fields themselves. So in order to see that, let's consider phi to be this bulk field to be a 5-dimensional massive Klein-Gordon field. So if we do that, we can immediately write a 5D Klein-Gordon action of this form. And here we're assuming the 5D metric to be a 5D Minkowski metric for simplicity. So root over minus g, which should appear here, is actually 1. So if we do that, and if we substitute this thing in here, then we can show that, and at some point the orthogonality of these exponential functions comes into play over this domain. And if we do all that, if we perform the y integral, then this S5 gets reduced to an effective 4-dimensional action. And this action looks something like this. Now, if you take the sum outside, you immediately recognize what this is. This is an infinite sum of individual Klein-Gordon fields, right? So each mode function is an actual field by itself, and its mass is given by a relation of this kind. And that is what we basically have, an infinite tower of 4D Klein-Gordon fields with masses given by this. So what are the implications of this? So firstly, if we put n equal to 0, the 0 mode of the tower is obviously equal to m0, right? The mass of the 0 mode. So that is what we actually observe in our day-to-day lives, if our energies are low enough. And an energy which is of the order at least greater than the scale of R inverse is actually needed to probe all the heavier modes of this tower. So this actually gives us, this actually provides us with certain detectable echoes of the higher dimension, if our energies are high enough. So that is why this is an extremely important concept as far as detection of these dimensions goes. So we're practically at the end of the talk. So this is going to be the final page. So here we are going to end with certain observations of the brain world. So what do we mean by the brain world? So, and we'll also see here a pretty intuitive explanation of something we left behind a long time ago. You remember the hierarchy problem of gravity, right? So we're going to see how higher dimensions actually help us, actually lead us to an intuitive explanation of the hierarchy problem of gravity. So a brain is basically a lower dimensional surface of a higher dimensional bulk space-time. So a brain can have, suppose, p space dimensions along with one time dimension, and we denote such a thing by, we actually call such a thing a p brain. So p is the number of space dimensions of the brain. So for example, our visible world might just be a three brain, which is embedded in a much larger bulk space-time. This is one possibility, right? So along with brains comes the concept of brain fields. So brain fields are defined as physical fields which are confined onto a brain, as opposed to bulk fields, right, which we defined earlier when we were talking about the Kaluza-Klein tower. So bulk fields could permeate all of space-time, and brain fields are confined primarily onto a brain. So this actually opens up a myriad of possibilities, right? So we can really go around and play with such scenarios. We can construct different worlds of stretched or warped brains, brains that intersect, and study particle phenomenology on such brains and in the bulk, etc. So it's only a matter of imagination. And of course, how closely our imagination can model our observable reality. That, of course, right? Now, here comes our role field. So this is the hierarchy problem. We revisit it. So in order to see how we can resolve this hierarchy problem within an extra-dimensional paradigm, at least intuitively, so let's look at this proposition. So this is the proposition. What if we actually live on a three brain, which is embedded in a larger bulk spacetime, and all the standard model fields that we can observe, like these leptons, quarks, gauge bosons, etc., these are all confined on our brain only. These are three brain fields, and only gravity can propagate through the entire bulk of the space-time. What is this is the case? Then, of course, this implies that the force of gravity is intuitively diluted, as gravitational flux can actually access all these additional dimensions, right? And this in turn implies that gravity, there is the possibility that gravity can actually be fundamentally as strong as all the other forces. But when you look at it from a four-dimensional point of view, it appears effectively weak because of the leakage of the flux through all these extra dimensions. So this offers a possible intuitive resolution of the hierarchy problem. And of course, to do this rigorously is a much more sophisticated thing, because it depends crucially on the particular brain world scenario which you're considering and lots of technical stuff. But this is a fundamental and intuitive idea shared by lots of extra-dimensional scenarios. Now, with that, we reach the end of the talk. So before I go ahead and show you my references, so let me thank you all once again for putting up with me and being so patient. So if I was unable to explain things in a more accessible way, so please excuse me for that, since I'm also kind of doing my best for someone who's completely new to these kinds of things. So thank you once again for this. And yeah, here are my references. So these three are Kaluza and Klein's original papers. And these two are excellent review articles, which are basically notes from TASI lectures of 2 subsequent years. And this is actually one of the papers that I'm having to study right now for my project. This actually provided the new impetus for extra-dimensional theories in 1999. This provides the basis for what came to be known as the Randall-Sundram brain-world scenario. And this is a very nice article, so don't be fooled by its name. This has lots of complicated calculations. So yeah, this was also pretty helpful, particularly for all those calculations. And if you refer to this one, I must warn you, you must be a bit careful, because this contains some typos and some missing terms and that kind of thing, which you have to verify for you. Okay, so that's it. Thank you.
Okay, thanks a lot. Thanks a lot, Orko. That was, for me, it was a especially epiphanous talk. I had very great moments of epiphany here. So without wasting more time, let's go ahead and see the questions. So I see Shagnik has a lot of questions. So Shagnik, if you'll unmute yourself and ask the questions. Kindly keep your questions short, okay? Shagnik, are you there?
Is he here?
Okay, if not, so then we can just read off from the chat.
Yeah. Okay. So Shagnik's first question was if I can rewrite the question by what was that? Changing the recipient.
So what's so special about the chi constant? Is it just a proportionality factor?
Okay, so let me go back to that one. Where did I write chi? Okay, so I guess he's talking about this one. Okay, so this is basically to make connection, as I said, So this equation already has the form of the Lorentz force law, right? But in order to connect it more concretely with our known form of the Lorentz force law, we have to make this kind of a transformation. So if we do that, then this thing comes out to be Q by MC, and this is our very familiar form of the Lorentz force law in curved spacetime. So actually, it doesn't, I don't think it has anything kind of special going on here. On the contrary, it could be considered kind of a limitation of this theory, because we have to put this forming by hand to make to touch with our the Lorentz force law that we are familiar with, to make this complete kind of identification. So chi right now, I don't think it has any physical significance, apart from the fact that, of course, it's a global constant of the motion. So chi was defined here, right? So this thing was chi. So chi is obviously a global constant of the motion. So if you're looking for any physical significance, I think that's it. It's a constant of motion. So that was the first
All
one.
right. Okay, so let's go to the second question.
Yeah.
So he asked that does the delta G tilde and delta G have any physical, so the determinant of
Determinant, yeah.
these two being same have any physical significance?
Okay, let's go there.
Or is it just a mathematical artifact?
Okay, let's see. Oh, okay. So yeah, it was somewhere like this. So yeah, so yeah, it actually is. So okay. So we have this form right here, right? So S tilde EH actually gives us gravity plus electrodynamics. And this is actually what's called Kaluza's miracle. And it's actually called that. So there is a proportionality constant. Apart from that, these actions are the same, because the proportionality constant of the action doesn't matter, as we know. So in order to do that, we needed this to be the case, right? And this is actually what happens when Klein's metric, we take the determinant of Klein's metric. And I think it has a very deep significance, but I'm not too, if I'm to be honest, I'm not too comfortable with that kind of thing yet. So it actually has to do with something, I think, like the fiber bundle of this additional spacetime that we're talking about. So it actually leads, in many Kaluza-Klein theories, it actually leads to the cancellation of all those gauge field-like terms once you take the determinant of the higher dimensional metric. So it just gets reduced to the usual 4D metric. But if you're looking for why it indeed happens, so I'm afraid I don't have a question for that right now. So, but this fact that it cancels out all the MUs in the metric determinant, this of course has a deep physical significance, because that is what allows us to connect to 4-dimensional. So I guess that's it for now.
Okay, I think that answers Sagnik's question. So
Yeah.
are there any more questions from the audience? Okay, I don't see any more questions. So I had two very short questions, Arko. Okay.
Yeah, sure.
Okay, so my first question is that in this prescription, I think you can also derive a formula for T mu nu, that is the energy momentum tensor, right?
Yeah, sure.
So if you can do that, so in associated with that, we must have some conservation laws, like the total divergence, of course, the covariant divergence of that being 0.
Yeah,
So
sure.
what can that in this picture, in this new picture, what can that mean? Do you have any idea?
Okay, so actually what we're getting after compactification, we're getting something like this, right? So this basically doesn't seem to tell us anything new apart from what we already know, because this is basically, if you extremize this action with respect to the metric, that gives us Einstein's field equations, right? And extremizing this thing with respect to the metric gives us the energy momentum tensor of the electromagnetic field. So I don't think in this particular context it gives us anything apart from that. But in a more general kind of scenario, in an even higher dimension scenario, or some kind of different compactification, of course, there is the scope that it can give some kind of different conservation laws or something like that. So in this case, I'm not sure if it gives anything else, because this is the crux of the thing, right?
Okay, so my last question is, it is to do with detections, all right? So in the, while addressing the bulk and the bulk fields and all that, so you addressed that gravity can actually access the bulk, and other forces live on these manifolds or branes, right? So we have the advent of gravitational waves, right? So can I expect any signature from gravitational waves, so as to detect these extra dimensions?
Yeah, actually, there are a few papers on that. Actually, there is a paper by my mentor himself, Professor Soumitra Sengupta, if I remember correctly. So, dimensions of extra signatures of extra dimensions from gravitational wave merge, from mergers of black holes and subsequent gravitational waves and stuff like that. But to be honest, I haven't gone through them myself yet. So, any answer I can give you at this point would be kind of, would be kind of convoluted. So,
but we can expect that to happen.
Yeah, we
I
can
think.
expect that, I think. And also,
Okay.
yeah, so gravitational waves is actually an application of general relativity, right? So it's not a core problem of that, it's an application. So in
Right.
5 dimensions, we can also expect 5 dimensional waves or something like that, which we can derive from a
Mhm.
5 dimensional theory of gravity. So of course that falls within the application part. So I
Right.
actually planned this talk to be more about the core concepts. So yeah,
Okay.
so
Okay.
that
Okay.
is within, that is beyond our scope.
Right. Thanks a lot, Orko. Thanks a lot again. So I think
Thank you.
that with this, we reach the end of today's session. So thanks everyone for joining. So we'll meet again. You'll get the